Zeqian is a PhD student working with Dr. Greg McFarquhar on cold-air outbreaks and boundary layer clouds. Before coming to OU, she earned an MS at the University of Utah and a BS at Florida State. Today, she'll be talking to us a bit about cold-air outbreaks and boundary layer clouds using observations from COMBLE. Is that how you say that? COMBLE?
Yeah, COMBLE.
Okay, and the Marcus projects.
Thank you so much for your introduction. Hi everybody, thank you for attending my seminar during this Thanksgiving break week. Thank you for the audience in this classroom, and thank you for the audience online as well. I will try to have eye contact with both the audience in the classroom and online. I will try to find the balance here. So the topic today is talking about the comparisons of environmental influences on boundary layer clouds, macro and microphysical properties over the North Atlantic and the Southern Ocean. We use the measurements from the COMBLE and Marcus campaign. So before I introduce what is COMBLE and what is Marcus, the first definition I'm going to introduce is the cold-air outbreaks, CAO. So the study of CAO can go back to several decades before, back to last century, 1970s, the GOES 2 satellite already captured the figures of the different locations with the observations of the CAOs. So the previous studies, they focus on how the fluxes heat changes during the cold outbreaks and how the boundary, how the cold shear shape, how the land shape can influence the cold air outbreaks. But how the cold air, how these boundary layer clouds connected to the environmental conditions, how the what's the relationship between the boundary layer process and what's the microphysics properties within this clouds are not well understood. So back to last decades, we have several campaigns conducted over the Arctic and the Antarctic as well. Among these campaigns, these campaigns list here, they sampled at least one good case of cold air outbreaks. And among these, the most recent one is the COMBLE, the cold air outbreaks in the marine boundary layer experiment. They conduct between the 2019 to 2020, 6 months measurement. And the future one, we have a season, the exciting news, we are going to have season next spring over the sub-Arctic region. Go back, at the previous studies, they already found that during the cold outbreaks, the boundary layer clouds can have specific patterns. At the very beginning, the cold outbreaks, the origins from sea ice, and the blow over the relatively warm ocean. First, they have the cloud straits rolls. They have open cells. They have cold cells. They are all mesoscale cloud structures. And nowadays we have more advanced satellites like MODIS. We can have a clear, more clear figures of these clouds. So I know many of the audience have these figures many times before. But I don't be surprised. I'm going to show these figures every year to remind everybody what is the cold air outbreaks. So at the first beginning, we have the very cold air origins from the sea ice, and they travel to the relatively warm ocean. At the very beginning, they have this, we call the cloud straits. That's the closest we can see. These roughly aligned with the wind direction. Or we can call these clouds as rolls, not these rolls. And also we have the open cell clouds. They have when they have cloud cells, but we can still see the cloud scale around these clouds. And as well, we have closed cells, the clouds are more stick together, they don't have much space between these cells. So yeah, we also have the polar lows, also very important for the synoptic background. So that's the satellite figures when we look down from the satellite. So imagine how when we travel along the cold air flows, at the very beginning to enter to the downwind portions. At the very beginning, the clouds are more like the cloud straits. It's more like the we can use the point here. Okay. Yeah, at the very beginning we have straight clouds. more rose structures, more like the most stratocumulus. As they blow, like travel all the way from the oceans to the land, we observe the more open cell clouds. So along with the cold flow, at the very beginning, the cloud top might not be very high, and they increase as the air flows around the. So when the cold air meets the relatively warm ocean, they have lots of moisture fluxes and heat fluxes transported from the underlying ocean to the boundary layer. So how to identify a cold air outbreaks? How to, like the first simple one is looking at the satellite figures to see all these beautiful cloud structures. Another one, and also the most common one, is using the M index, which is the potential temperature differences between the sea surface temperature and the weir mixed boundary layer. There are some discussions how to define the weir mixed boundary layer top. Like some studies use 700 hectopascal, but some studies use lower level. Like for the most recent one, the Gears paper and his students Christian Lechner's paper, like they used 850 for the COMBLE measurements. So here we use the same definition as there. And for some locations, is for example, for COMBLE, they limited their wind directions for this range because they wanted to make sure all the wind blow origins from the sea ice. There is another definition I'm not applied here in my research, is using the Cold-air Outbreaks height. When the CAO is pressure level height is lower than 800 hectopascal, defined as the Cold-air Outbreaks. So this study only uses the positive M index here. So what's the counterpart, or say what's the enemy of the cold outbreaks? So it's the warm air intrusions. So they are like stratified moisture southerly flow and might carry lots of moisture, heat, aerosol into the Arctic. So from the conceptual figures, when we have the warm air intrusions, the convection will be deeper, and we expecting high cloud tops. And the definition of the WAI is also from the Lechner's paper, like say, it's quite the opposite way of the CAO. When the CAO have the relatively warm sea surface, but the relatively colder air flow in, but the warm air intrusion have the relatively warmer outflow, warm upper layer flow, and a relatively colder surface temperature. Here is an example, one example before the CAO and WAI. From Lechner's paper, he used the ERI5 data to draw these figures to show the sensitive heat flux. Like when the CAO, they have the most positive, very strong sensitive heat flux. When the warm air intrusion, they have a negative one. And I picked these two cases. One shows the cold air outbreaks. We have a relatively lower boundary layer clouds and most open cell clouds. For the warm air intrusions, we have more deep convection clouds, more like the frontal system clouds. For this study, we only focus on boundary layer clouds within the CAOs, so we don't consider the WAI right now. So for the motivations why we care about boundary layer clouds and why they're so important, it's like the relationships between the boundary layer clouds and how they vary based on the environmental conditions and different locations. It's not well understood, but it's very important in the Earth model, system models. And the convective boundary layer clouds over the high latitude during CAOs can impact the Earth's radiative balance. But it must be presented accurately in the models. But the previous observations are very limited. Like boundary layer clouds during CAOs over the North Atlantic are very common. But the relationship between the boundary layer processes, the convection, the precipitation with these clouds is not well known. And the CAOs also can happen in the Southern Ocean because Antarctic also have large area of sea ice. The interesting thing is, compared to the Southern Ocean compared to the North Atlantic, the Southern Ocean is more pristine, like they have a different aerosol background, so it will provide us some interesting observations. So go back to these figures among these campaigns. the option for us is very limited. So for the Southern Ocean, we choose the markers, and for the North Atlantic, we choose the COMBLE. These two campaigns, the markers conducted from 2017 October to 18 March next year. As a combo, like the mirrors from the winter to spring. So we should mention that the first one, these two campaigns mirror make observations in different seasons. So markers, we don't have winter season observations. So that's the one major point. And another one is the markers, they have icebreaker aurora, like travels from different locations. So it have a large latitudinal ranges compared to the COMBLE. While the COMBLE, we have the main side and the underneath, it's fixed. So it measures the clouds mostly to the downwind portion of the cold-air outbreaks. But the markers, they have more like more variable conditions. So at the very beginning, let's introduce three environmental parameters. The first one, we mentioned before, is the M index, which describes the intensity of the cold-air outbreaks. The larger the M, the more intense of the cold-air outbreaks. The second one is lower tropospheric stability. The LTS, it can estimate the potential for the deep convections. The last one, the estimated inversion strength, it describes the inversion strength of the boundary layer. So this figure 1, shows the relationship between the LTS, EIS with the M. Like all the COMBLE measurements are listed on the left column, all the markers measurements are listed on the right column. So the markers A and B shows we see the negative correlation trend between these two parameters. Here the R equal is the Pearson correlation coefficients. So both LTS and EIS shows negative trends. So that means when the cold air outbreaks is very strong, we have lower potential for deep convection. Also, we have lower inversion strength. The markers on the right column show the similar trend, but the difference is the markers should have within the orange circle, the observations is more spread. It's probably due to the Southern Ocean has more variable conditions compared to the COMBLE. Comparison these two campaigns, when the M is larger than 5K, that means the cold air outbreaks is very intense. So all the COMBLE's observations are red solid lines, or the markers in blue lines. So the markers, they sample more intense cold outbreaks. As well, they have a lower cloud top temperature. For the cloud-based temperature, they don't have significant differences. For the markers, they have stronger LTS as well as EIS, which means they have stronger boundary layer inversions. And we should also mention that, although the COMBLE sample more intense cold air outbreaks, but the markers looks like they have lower above surface temperature. So I need to mention that the surface temperature here is not the skin surface temperature. So it's the lower the level the sounding can measure. So actually it's the above surface temperature. So let's look inside what the cloud structures vary with this M index. So here is the CFAT is the controlled frequency by altitude diagrams. So the CFAT of radar reflectivity shows how the radar reflectivity's frequencies change according to different height levels. So for each subplot, is divided these plots into different M ranges. For example, for the figure A, that means when the M is positive but less equal than 2.5K, so we have 181 hours measurements. These CFATs show the highest cloud height can reach around 8 kilometers. As the M increased from left to right, the highest cloud top decreased as the M increased. For the markers, we have the similar trends. Also, we need to mention that, like, for these two campaigns, the DBZ values are, like, they have huge differences. That's because they use two different kinds of radar. For the COMBLE, they use the Ki band radar, and for the markers, they use the W band. So the wavelengths of the radars are very different. So that's why they have very different radar reflectivity values. And the next one is to have the Doppler velocities ranges with the M index using both COMBLE and the markers measurements. So for the ground-based measurements, like both COMBLE and the markers, they have the ground-based radar. Like when the Doppler velocity is positive, which means the objective is moving away from the radar. When it's negative, which means the objective is moving toward the radar. So both COMBLE and the markers shows during the CAOs, we have negative chance of the Doppler velocity, which means precipitation. So in order to prove this hypothesis, we also here attach the ring gauge measurements from COMBLE. So we see when the M increase from very negative to positive, we see the positive correlations between the precipitation and M index. But unfortunately, for the markers, the measurements and the rainfall measurements are very bad. Like we cannot use like it's very easy to be polluted by the sea water. So it's not suggested to use the rainfall measurements from the markers. So like another thing that similar CFAT is using for the spectral width. So spectral width is like the distribution of the Doppler velocities within a single radar pixel. So when the spectral width is more broad, which means the turbulence and shear is more strong. Like we see for when the M increased from 0 to like over 10K, like we see the increase of the spectral width. But for the markers, it's not so strong as the combos. So we may guess, first one, probably the markers, they don't have, like within the clouds, the turbulence is not so strong as the combo. Another one probably is caused by the different cloud phase. So when is for example, we can guess that when the combo is dominated by the single phase and the markers is dominated by like mixed phase, so it can also cause differences in the spectral width. For the surface fluxes measurements, we use the ECO system, which is the AD correlation flux measurements system. For the combo, we have the ecosystem to show when the M increase from negative to positive, we show the increase of both the latent heat flux and the sensible heat flux. Unfortunately, again, for the markers, we don't have the ecosystem. So now we look at how the boundary layer structures vary with different M index. Here we show the average profiles of the relative humidity, and when the markers show in blue and the COMBLE in red, the transparent pocket here shows the variations, the 70% percentile and the 25 percentile. And the horizontal average line is the average boundary layer height for the both COMBLE and for the markers, COMBLE in red and markers in blue as well. We can see the average boundary layer height can increase when the M is very negative to all the way to like around 2 kilometers when the M is very positive, when the CL is very intense. We also see that, also need to mention that when the M is so strong, we see like for the markers, there are more moisture compared to the COMBLE. Another way to see the boundary layer structure is using the average profiles of the temperature as well as the dew point. The temperature is in blue and the dew point in the yellow. Similar, like we have several horizontal lines to show the 700 Pascal, 800 Pascal, and averaged cloud top height and average cloud base height. The key point here is when the M increased from 0 to very large, the surface moisture increased as well. And these trends were observed for both COMBLE and markers. The difference between these two campaigns is during the markers, when the M is larger than 10K, we have seeing a very large, dry and very obvious dry layers above the boundary layer. So that might can inhibited the boundary layer for the clouds to deep convection. But for the markers, it's more moisture compared to the COMBLE. So next step is the cloud phase distributions. So for people who are not familiar with the LiDAR measurements, the one of the LiDAR measurements is the depolarization. When the dipole is 0, which means the objective is more superior. So for the liquid cloud droplets, we tend to have very small, very near to 0 values. But for ice crystals, we will tend to have more large dipole values. So we, based on Mace and Portate 1980s paper, they divide all the measurements with where more ice dominated and more liquid dominated to see, or they found that around the 0.03, when the layer is, when the dipole is less than this value, the clouds are more likely to be supercritical, to be more liquid dominated. When the dipole is larger than this value, it's more likely to be ice crystals. So based on their algorithm, we see for both cloud top and cloud base, when the cloud base temperature is below 0, we still have see the supercritical water at the cloud base. As the temperature continue to decrease, we see the increase in ice crystals here. And here is something cause some discussions for the ground-based LiDAR measurements. The cloud top measurements probably is not reliable because the LiDAR can be attenuated very quickly. So for example, for boundary layer clouds, when the cloud top is 4 kilometers, these results is not reliable for the cloud top. So for this research, we only focus on the cloud-based phase. Here, for these the statistical results to show how the ice and the liquid distributed. But for the COMBLE cloud base, we see the slightly higher percentage of the ice, and for the markers, these numbers are very close to each other. We can see it's not so statistical significant. Another algorithm is from the atmospheric research measurements. The evaluated product results shows both COMBLE and markers, especially for COMBLE, they have more ice and compared to the liquid. So, but for the markers color base, still the numbers here is not so we don't see huge differences here. And then here the other figures in this table and these figures show how they derive these products using SHUP 2007 paper. At the very beginning, they use the LiDAR measurements, the dipole and backscatter to generate to say, okay, when the liquid phase, we have a relatively lower dipole but a relatively large backscatter. As for the ice, they have a large dipole but a relatively lower backscatter. So based on this, it already adds the Doppler velocity algorithm and as well as the radar reflectivity to divide this cloud phase. So the summary here is compared to these campaigns, the COMBLE, they have higher above surface temperature, although they sample more intense cold outbreaks, but they have a lower cloud top temperature and smaller boundary layer inversion compared to the markers. And the cloud phase is very tricky here, so we need to further investigation. So that's so far, this is the first part of my research is focused on the macrophysical properties. So the next step is for the retrieve the microphysical properties of clouds. For this part, I'm still working on that. So the results is not the final results. So it's probably can cause some good discussions here. And the final goal is explore their correlations with the meteorology conditions. Because for the COMBLE measurements, we don't have the aircraft measurements, we don't have in-situ measurements. So the only ground-based we can apply probably is common one is the radar, LiDAR, and the radiometer. So At the very beginning, I used the radar-based retrievers based on Dong's paper in 1995. Like they assume the cloud droplets number, concentration, and size distribution are constant with height. So they find the relation between the size distribution, number, concentration. The relationship is between the radar reflectivity, and so based on their method, you can derive that the number concentration can be expressed by the liquid water contact, the water density, and the radar reflectivity. This value is assumed to be constant. The liquid water contact can be derived from the radiometer, the liquid water path, divided by the cloud thickness. And once we have the values for n, we can derive for the effective radius values here. However, the results here show like between the CAO in blue and the non-CAO in orange, their difference is not so huge, but their trend are very similar. So the water droplets effective radius increase with height is due to the condensational growth, and the eventually decrease is probably due to the collision and coalescence near the cloud top. But we expecting like there should be huge differences when the CAO occurs and compared to non-CAOs. But based on these figures, like we don't see large differences here. And the red text is here because the lower the level, the radar can measure is 150 and 160 meters. So when the cloud height is so light, precipitating. So we divided when keep this cloud layer base at 160, and another one is remove this condition. Then I choose another algorithm is also based on radar-based measurements. Like Dong and Mays in 2002, they derive the relationships between the effective radius and with the radar reflectivity. Like same here, like we don't see the huge differences here. And there's a third one for the radar-based retrievals, and I won't like put too much time here, like to say to describe the algorithm here, but the result here still like compared to the others, like it's not a significant differences between the two conditions. The future ones probably will use the LiDAR-based retrievals. And the problem is for both COMBLE and markers, the LiDAR is a micropulse LiDAR. They don't measure the extinction coefficient directly. They only have the total attenuated backscatter here. So what I need to do is to derive the backscatter coefficient using the LiDAR equations here. So that's the future plan. And one problem is like for the COMBLE and markers, so we don't have institute measurements. So when we get the retrieved results, how should we know it's reliable? How confident we can see, oh, this is accurate. So in the future work, probably I will use the previous campaigns. We should have both the ground-based radars and also the institute measurements to apply this method to using the previous observation to see, okay, how this algorithm looks like. After that, we will reapply our method to the COMBLE data as well as the markers data in the future. So that's all my stuff today. I'm happy to take questions now. Thank you.
Forms and the questions. If you have questions online, feel free to use the chat or raise your hand online. Does anybody in the room have any questions? I have a question. So, not being as familiar with this part of the world, I was kind of surprised. I found it counterintuitive that boundary layer height is as deep as it was in these strong cold air outbreak cases. To me, it sounds counterintuitive to some very deep vacuum. I understand that you're seeing more turbulence in these things. But can you speak to why boundary layer might be so much cheaper in this stronger cold?
That's a very good question. Yeah, like I haven't think about it before. And that's a very good point. I don't have like very I don't have answers right now, but probably we can like I'm thinking about what method we can use to yeah, sorry for that. Yeah, probably I need to think about it later. Yeah.
Just curious.
Yeah, that's a very good point. Please. Mm-hmm. Yeah, I got these conclusions based on these figures because we see like more negative changes of the Doppler velocity occur during the COMBLE, but for the markers, it's not so obviously. And so one guess is that probably for the markers, like the clouds is less precipitating. And another problem is for the markers, like it's not designed for the cold outbreaks. So the observation is very limited. So you can see the differences here when the M is larger than 7.5, we only have 1 hour's observations. But for the COMBLE, we have more observations. So probably the marker is not so representative for the Southern Ocean environment. So just based on this, the data we have now, so that's the hypothesis. But it's very good point here. Yeah, but unfortunately, we don't have the good uniform measurements from markers. Otherwise, we probably will be more confident to draw this conclusion. But thank you so much.
Okay, thanks, Hazel. That was a nice presentation. Can
Thank you.
Say a little bit about what you hope to get out of CAESAR? You know, CAESAR is upcoming, using an aircraft to sample these cold air outbreaks rather than the remote sensing instruments you've been looking at. But can you talk a little bit about what you hope to get out of these data and how they complement with what you've already done using the COMBLE data?
Thank you so much. Yeah, like the CAESAR, like it's quite different from the COMBLE. Like they have, Greg mentioned that we have the aircraft flight. And the one thing, like the first advantage is we have more in-situ measurements. Like we can see actually what's going on inside of the clouds. That's the one advantage. Another one is, compared to the COMBLE, which the site is fixed, the CAESAR, like they can track the cold outbreaks. Like they can do, we can do the Lagrangian, I'm not sure, the measurement observations. Like we can see how the clouds evolution along the airflow. Probably you can have a different kind of point of views for observations.
Here, one more.
I saw Chin raise her hand.
Hi, Hazel, you hear me fine?
Hi. Yes, loud and clear.
Nice talk.
Thank you.
I am a little bit curious about the cloud phase for Marcus and COMBLE that you showed the chart over there in one of your slides. Yeah, so here you listed ice cloud and liquid cloud. Looks like they don't add to be 100 over there. Do you have, it's okay to go to the next slide, please?
Oh, I got what you mean here.
And I was like to say, are they mixed phase clouds or like what happened over there? Yeah.
Yeah, for the original VAP product, they not only focus on the ice and the liquid, like these figures show here, they also have the mixed phase, drizzle, rain, snow. So that's why these two numbers, they don't sum up as 100%. Sorry for the confusion. I should have mentioned earlier.
This is for the cloud or for the hydrometer?
Hydrometer.
Okay, this is the same precipitation type, right?
Mm-hmm.
Okay, I see. Thank you so much.
Thank you. Thank you for your question.
Any last questions? Okay, well, let's thank our speakers.
Oh, thank you so much.
And we have a handful more seminars. They're on the calendar on the BLISS website. So keep with us through the end of. Happy Thanksgiving.